Okay, good afternoon. My name is Alexander Feher, and I wish you a happy, prosperous, and healthy new year. So I would like to introduce today's speaker, Professor Vladimír Zeleniak from PJ Šafarík University in Košice, Slovakia. Vladimír Zeleniak is an expert in the field of inorganic chemistry and chemistry of porous materials, where he focuses on new nanoporous sorbents based on periodic nanoporous silica and organic complex compounds known as metal organic frameworks. He published the result of his work in more than 120 original scientific papers, such as Dalton Transaction, Inorganic Chemistry, Applied Surface Sciences, ISC, Advances, Scientific Report, and other. He has more than 2,400 citations. He is a leader of the Triangle Top Scientific Team in Slovakia. A significant scientific contribution of the Professor Zeleniak is the use of ordered mesoporous materials like mesoporous silica and metal organic frameworks as drug delivery system, and also for advanced separation and storage of technologically scientific gases, significant gases like carbon dioxide, methane, or hydrogen. For his research, he was awarded in 2019 by the Prize of Scientist of the Year in Slovakia. In 2020, he became a member of the Scientific Advisory Board of the European Research Institute for Gas and Energy Innovation. In the frame of this cooperation, he focuses his interest on the use of porous materials in gas management, especially carbon dioxide separation and hydrogen storage. The topic of hydrogen and hydrogen technologies is going to be presented in following lecture given by Professor Vladimír Zeleniak. So Vlad, the stage is yours.
Thank you, Professor Feher, for very kind introduction. I will share, just a moment, I will share my presentation. Now you should see it. Can you see it, please?
Yes, we can see it.
Professor Feher, can you see my presentation?
Yes, we can see your presentation.
Yeah, okay, thank you. So first, I would like to thank organizers for giving me opportunity for this presentation and for this talk. As Professor Feher said, one of our research topic is gas storage and gas separation. And at present, we are focusing on hydrogen storage. As all of you probably know, in 2020, European Commission or European Parliament voted, and European Green Deal was introduced to life in Europe, which means that in 2050, Europe should be climate neutral and no net carbon dioxide or other greenhouse gases emissions should be present. So one of these in this Green Deal, of course, it has some political decision, it has some scientific decisions. However, it's not possible to reach this goal only with electrons or only with molecules, but for Green Deal, both complementary roles of world of electrons and also world of molecules has to be considered. So this is also new view on hydrogen, which is considered as energy gas. For example, at present, about 20% of energy in Europe is from electrons, and 80% is from molecules like natural gas. So both these approaches has to be combined in future carbon neutral economy. And as I said, people sometimes don't realize that it's new look on hydrogen. Historically, hydrogen was viewed as chemical substance. One of the basic chemical substances which are important for all chemical industry, which are important for our lives, but which are important for production of different types of products, chemicals, which we use like antifreezing agents or so on and so on. So it was considered as chemical substance. Now, new view is to consider hydrogen as energy carrier. So it has some hidden energy which we have to release and use this energy, let's say, for example, in fuel cells to produce electricity, to produce electrons, and in different applications. And these applications of hydrogen energy can touch different sectors of our human life, from transportation, not only car or urban transportation, but most main challenge is transportation of heavy transportation like trucks, like shipping, because batteries don't work in such transportation. So hydrogen is challenge in such kind of transportation. But hydrogen energy can touch also the other sectors of human life, like housing, like energy in industry, and so on, and so on. So there are different approaches on view where the hydrogen can be used, where the hydrogen can be used for production in industry, like in steel industry, like in cement industry, and so on, and so on. Politicians and also maybe scientists divided hydrogen according to colors. I'm a chemist, and for us, for chemists, the hydrogen is still the same. Either it's blue, or it's green, or it's gray. It's still molecule H2, and it has the same properties. Anyway, in politics or in life or in Green Deal, the hydrogen is divided to green hydrogen, blue hydrogen, and gray hydrogen. Green hydrogen is, for a long time, the hydrogen was produced by conventional way, which means steam reforming using either coal or natural gas. This hydrogen can be called either gray, or during this process, so-called syngas is produced. Syngas, it's a mixture of carbon monoxide and hydrogen. And if this and the carbon monoxide is oxidized to carbon dioxide, so if we separate carbon monoxide or carbon dioxide from hydrogen and use this carbon dioxide in further processes in production of the different chemicals, so it's called carbon capture and utilization or we can store separated hydrogen or carbon dioxide in some underground formations, and it's called carbon capture and sequestration. So when steam reforming is combined with CCU or CCS process, it's called blue hydrogen. If it's not combined with these processes, it's called gray hydrogen. And green hydrogen is preferred now in Europe. Green hydrogen is produced by electrons from electrons and electrolysis, electrons from different solar farms or from wind turbines. So this is called green hydrogen. However, I know that the European Commission is forcing and pushing this green hydrogen. However, it's not universal solution, because maybe it will work in countries which are near the sea. They have offshores, but in countries like here in Slovakia, we are a relatively small country, and we can produce enough hydrogen only like a green hydrogen. So surely in future we have to combine it with blue hydrogen. And now also some people try to introduce a new color of hydrogen, which is called white hydrogen, which means this hydrogen is produced by plasma gasification of waste. So different waste produced by human society, either in households or in offices, or this waste is gasified in a plasma arc. This white hydrogen is considered as ecological one, maybe because it is connected with waste and using the waste. But anyway, during this gasification, different gases are produced similar like in steam reforming. So there is carbon dioxide, there is hydrogen, there is maybe some chlorine, there is some halogen compounds. They can be sulfane. So in my view, it's not the one ecology is that we use the waste. But in composition, we are in the level of gray or blue hydrogen. If we want to think and consider hydrogen economy, we have to produce large quantities of hydrogen. As I'm sorry, I will go back to previous picture. I forgot to mention, as you can see on the left upper corner, at present only, in near history, only 4% of hydrogen was produced by electrolysis, and 96% were produced by from fossil fuels. And now it has to be changed, because green hydrogen is produced by electrolysis. Anyway, there is another difficulty, because if you want to produce hydrogen by electrolysis, you need pure water. And if you want to produce 10 tons of hydrogen, you need large quantity of pure water. And it's another problem. So this, as you can see, the production of green hydrogen, it's not so linear, but has different problems. But hopefully till 2050, these problems can be solved. And when we produce large amount of hydrogen, so we have to store it. And how to store hydrogen? So we have two possibilities: to use some cylinders or store it without use of, I call it without use of advanced materials. And the other possibility is to use some advanced materials for hydrogen storage. So hydrogen can be pressurized like a gas. It can be liquefied like a cryogenic liquid, or can be adsorbed or absorbed in different type of materials. First two processes are most mastered at present because pressurizing of gas, you are experts in this field. more than me. And pressurized gas, this technology is very well known. Also, liquefaction of hydrogen is very well mastered because space industry use it in large quantities. So these technologies can be directly transferred to hydrogen storage. And the truth is that at present, there are the only two available technologies which work. For example, in cars, hydrogen cars like Toyota Mirai, we use pressurized hydrogen, and the pressure is hydrogen tank is 700 bars. It really very high pressure, and it has some safety risks. If you consider, we have also, we use natural gas also in cars, but this pressure is much for lower, about, I'm not sure, but maybe about 200 bars. So 70 bars, it requires a special container constructed from special materials, and it's not easy tasks. So also the price of these cars is much more higher, not only due to fuel cell used, but also due to these expensive containers. The other possibility for storage of hydrogen is liquefaction, storage liquid hydrogen. And this way now at present is very developed. And I read that companies like Daimler, Mercedes-Benz, and Linde cooperate to construct refueling stations to hydrogen cars, but these refueling stations will not use pressurized gas, but they will use hydrogen as a liquid, and this gas will be then transferred to storage tanks of the cars. So the other possibility, the advantage of liquid hydrogen is higher density. Density of liquid hydrogen is about 70 kilograms per cubic meter, but density of pressurized gas at 700 bars is about half. So of liquid nitrogen, 40 kilograms per cubic meter. So these are two technologies which now work. Of course, we have also the other possibilities, and to store it in materials. What is important, and what I would like to point out is when we talking about storage materials, we have to consider gravimetric storage capacity. Because as you can see in this graph, I'm sorry, now I notice that it's in Slovak, but when you see the green columns, when considering gravimetric storage capacity, hydrogen store 2 or 3 times more energy than conventional fuels like methane or petrol or benzene or methanol. When considering volumetric capacity, the hydrogen is not favorite in this field. So we have to develop materials where hydrogen will be stored with high gravimetric capacity. And as I said in one of the previous slides, this approach can be achieved by either physical adsorption process or by chemical absorption process. Physical adsorption process is used by porous materials like metal organic frameworks, zeolites, carbon nanotubes. These materials have very large surface area and large pore volume. For example, if we consider pore system in some zeolite, 1 gram of zeolite can have channels or these pores with length 4 times longer than distance from Earth to the Sun. And 1 gram of metal organic framework can have surface area 1 or 2 times larger than soccer field. So this is this is advantage of these materials, and phenomenon adsorption is special, is unique. And when you fill pressure cylinder with metal organic framework, you can put inside this cylinder several times maybe 10 times more gas than in pressurized in empty cylinder due to phenomenon of adsorption. So this is the idea of use of such materials. Metal organic frameworks we are also studying and dealing with. We discovered in 1999 by Omar Yaghi from United States, and he prepared porous zinc terephthalate. So he combined zinc ion with 1,4-benzene decarboxylic acid, terephthalic acid, and he prepared porous structure. And he also managed to change terephthalic acid to other decarboxylic acid, and he prepared series of MOFs, so-called isoreticular MOFs, which have same symmetry but different pore volumes. And you can increase pore volume, and these yellow spheres on the picture show the volume which is available for gas adsorption in these materials. Another or in synthesis of MOFs, we are also dealing with the synthesis of new MOFs. You have to look at so-called secondary building units. So it's a clusters of metal ions, which can be triangular, which can be tetrahedral, octahedral, they can have different polyhedral shape. And you connect these secondary building units with organic linker, and you form final porous structure. Such materials, of course, we characterize them by relevant techniques or techniques I will show you later. And another property of these materials is, so some of them have so-called breathing effect. So the structure can open and close applying temperature or applying pressure. So the picture on the right, you can see adsorption isotherms of carbon dioxide, methane, or nitrogen on 1 mil compound. And you can see that for carbon dioxide adsorption at 278 or 288 degrees Kelvin, you can observe big adsorption step and then desorption step. So this compound breathe. It takes inside the structure carbon dioxide, but not nitrogen or methane. So you can use this process for separation of gases, so-called pressure swing adsorption, and you can separate quantitatively carbon dioxide from the other gases. So another possibility of use these MOF materials. In our department, we are working with MOFs, which we named UPJS. At present, we have 12 new structures, UPJS molecules. We use for their synthesis methane tetrabenzoic acid. Some of the structures are very unique because they imitate natural minerals. So a complex structure, but when you view on this structure some simple way, so such structure can imitate either diamond or fluoride, which is calcium fluoride. So they have some beauty from a scientific point of view, but also the structures are porous and they can absorb different gases. This is only just example of different methods we use for the study, because when you synthesize such material, the pores are occupied by solvent molecules like water or dimethylformamide. So you have to remove the solvents from porous structure. You have to remove it gently because otherwise the porous structure can collapse. But after removing, the sample is stable up to 400 degrees Celsius and can be used for gas adsorption and separation. And here is an example of the gas adsorption of different gases. On one of the MOFs, it's calcium version of one MOF, and the absorption of nitrogen, absorption of argon, carbon dioxide, methane. Some of them are cryogenic, of course. Absorption of carbon dioxide can be done in cryogenic conditions. And we use also these materials for hydrogen adsorption. Here you can see on the graph you can see hydrogen adsorption on calcium modify or calcium version of one of our compound. Absorption capacities at 1 bar are about between 2 and 3.6 weight percent of hydrogen per 1 gram of adsorbent. At a high pressure up to 100 bars, it's about from 7 to 10 weight percent. 100 bars is considered as a safe solution for transportation. At present, we use, as I said, 700 bars. But for the future, this optimal limit is maximum 100 bars. Disadvantage of this material is that its absorption, physical process using van der Waals forces. So this absorption is at cryogenic temperatures, at temperatures of liquid nitrogen. Now the scientists and also we focus on increasing this temperature, and the important is increase the absorption energy, because usually absorption energy is of hydrogen on MOFs is between 5 to 10 kilojoule per mole. If we manage to increase this absorption energy to approximately 20 kilojoule per mole, such materials can absorb hydrogen also at ambient conditions, which will be this big challenge. Here, this is only just to show you that last paper, interesting paper was published in Science Journal in April 2020, and it is dealing with NU, Northwestern University material, which has absorption capacity 14 gravimetric weight percent per gram, which is far above all other known materials to be used for hydrogen storage. And also some practical application, also some trial or some pioneering project were made where most were used for transportation. It was not hydrogen, but natural gas. But there was a project, EcoFuel Asia Tour, where most were used in tanks of car. It was some Volkswagen, and there was tour from Berlin to Bangkok in Thailand, and this tour showed that such container had 30% higher storage capacity compared to conventional pressure, and range of increased approximately about 20%. So some pioneering projects are already done. We will see what will be in future. The other possibility for storage of hydrogen are hydrides, either organic hydrides or inorganic hydrides or metal hydrides. It's not a new story because, as you know, some metals like palladium is able to absorb, so it's not adsorption, but it's absorption, it's chemical process, can absorb up to one volume of palladium can absorb 700 volumes of hydrogen. And not only palladium, but also the other metals or intermetallic compounds are able to absorb. One of best known is lanthanum nickel compound, which is used in batteries for a long time. It's very known. So this approach also at present is starting. History is revealing, and new materials based on metal hydrides and for absorption of hydrogen into structure of metal hydrides are developed. In this field, so here you just can see different types of metal hydrides, and they either volumetric or gravimetric capacity. So as you can see, metal hydrides has lower gravimetric and volumetric capacity than MOFs. But on the other hand, this absorption and desorption of hydrogen can be done at ambient temperatures. So absorption can be done in temperatures about 0 degrees and desorption in temperatures between 100 and 200 degrees. So these metal hydrides are now also considered as in future hydrogen economy for hydrogen storage. We have cooperation with Professor Tomáš Brestovič from Faculty of Mechanical Engineering in Košice. He is a mechanical engineer, and he constructed a metal hydride compressor with heat pump. In this compressor, he has 2 cylinders, which are filled with commercial metal hydride. One cylinder adsorbs hydrogen. You know that adsorption is exothermic process. So absorption is extraordinary process. So the heat which is evolved, he used for the other cylinder to just desorb the hydrogen. So it's such kind of combination, and in cooperation with him, and also with Professor Saxel from Academy of Science, we try to prepare a new, more efficient intermetallic compounds for this hydrogen adsorption. And the other approach we are using is combination of MOFs and hydrides, because MOFs show so-called nano-confinement effect. Using confinement of different compounds into nanoporous materials, we can decrease temperature of melting or temperature of hydrogen desorption from these materials. So the other approach is to put magnesium hydride or borohydrides into our MOFs, or we use also porous silica supports. And also we use some metal doping, 1–2% of nickel. And by this way, we try to reduce temperature of the hydrogenation of let's say, magnesium hydride or some borohydrides. So as you can see, hydrogen evolution from borohydrides is about 186 and 300 degrees Celsius. And by nano-confinement, we are able to shift this evolution to lower temperatures. So this is the other area where we are, or these different type of materials we are starting. So we are scientists, we do some basic research, or maybe sometimes also application research, but we are also interested in application of hydrogen technologies. And this is one of example. Now we are starting project. As Professor Fer said, I'm in a scientific advisory board of ERIC, which is European Research Institute for Gas and Energy Innovation, and in cooperation with them and Košický samosprávny kraj, Košice self-governing region, we got the project where there are 5 countries: Germany, Italy, Upper Austria, and Romania and Slovakia, for application of hydrogen technologies in real life. And what we want to do, we want in the Košice self-governing region to try to install green hydrogen production and storage. So Košice self-governing region has its carbon dioxide is considered by European Commission as carbon dioxide intensive region, and it has industry, steel production, US Steel Košice. It's the red point on the map, left bottom. Cement plant Turňa and coal power station Vojany. And this Vojany was now closed. It's a coal power station, it has to be closed. So now idea is to turn it into some solar farm there to produce green hydrogen and to store this hydrogen either in some underground formation. And we have also partner Nafta, in translation it's petrol. They have some storage availability near the Vojany, and also SPP Distribucia, which is gas distributing company in Slovakia, and with them we will try to transport of hydrogen through pipelines. So this is not research, it's application of known technologies, but I wonder how it works. So maybe in 2–3 years, I can tell you that if this Green Deal is okay or not. Okay, and so I'm going to conclusions. So when talking about hydrogen, it seems that the question is not that hydrogen economy will be, but when, because it's Green Deal. There is a political will which can use various tools to force the society, the people, to Green Deal, like taxes and so on and so on. Industry, companies may be forced by taxes. If you don't use green technologies, okay, you have higher taxes. So it's reality, and the world is changing, and we have to try to live with this. Of course, hydrogen is not the only energy source. It can be. It has to coexist with other energy sources like batteries, also natural gas. The problem is sustainability, because if only Europe will be green and use, let's say, hydrogen, price for hydrogen production and technologies is high. The cost of the products will be higher than from the other world. So there is Europe couldn't be competitive. So in this way, it's important that the similar politics will be around the globe. Also, we have to be some pragmatic people. I took one example from biodiesel. I read somewhere that production of 1 liter of biodiesel costs or consume 1.1 liter of normal diesel. So it has no logic such. So it has to be also in hydrogen technologies that the sustainability should be considered. At present, hydrogen technologies are expensive, but I wouldn't aware of this because also solar cells were expensive. They come from space industry. And now we use these solar cells on calculators, on houses, so the price went lower. The same I expect for hydrogen technologies. And not to talk about hydrogen and its advantages, so if I want to be objective, I have to look also from the other side. So as a conclusion, I give only last two notes or two examples. So first example at marginem. In this article, which I read in Financial Times, it was in March 2020. It was time when the Corona crisis started in Slovakia, so I had time to read different journals. And as there is written or calculate that the world must look beyond the sun and wind for hydrogen, because if we want to produce large quantities of hydrogen, we need large space, large land area, and there is such calculation. So if you want to produce 7 terawatt hours of energy, you has to cover 40% of United Kingdom land by these photovoltaic panels. So it's impossible. And the other is from Slovak. It's from Slovak newspaper called SME ad marginem 2. And you know that, of course, the Olympic Games in Tokyo were canceled. It should be 2021. And the Japanese were proud that they make green Olympic Games, and it should be hydrogen games. The village should be power for Olympic village should be from hydrogen fuel cells. Cars should be hydrogen cars, and so on, and so on. And the article from our newspaper, I will translate it because it's in Slovak. It's written: the Japanese are proud of ecologic Olympic Games, but they are building coal power station. And if it's true, in this article was written that they plan 22 new coal power stations, and 5 of them should be open in 2020. I don't know if it's true. It was some crisis, but this is what I said about sustainability. If only Europe will be green and the other world no, so Europe will have big problem with competition with other countries. So thank you very much for your attention, and it's the end of my presentation.
Okay, thank you very much, Vlado, for a nice lecture. Unfortunately, we have no time for questions. So if a participant has some question, please ask Professor Zeleniak through email. So thank you again for Vlado and for participants, and bye-bye.
Thank you. I'm sorry to spend longer time.